a quite exciting section of the work. Green's theorem, Stokes' theorem, and Divergence theorem. In order to understand the language of Green's theorem and Stokes' theorem and Divergence theorem, we first have to cover a few basic definitions. So I'm calling this, in my notes I called it the preamble to the vector calculus theorem, so let me do that here as well. Oh, I'm still on dark blue, I should change. How about some purple? Yeah, okay, preamble. This I'm just my wording to the vector calculus theorems. Everything connected? Yes. Okay, and I am recording and the microphone is plugged in. Okay, right. And I did hand out the registers. I'm actually more in control than I expected. Okay. When people refer to, when textbooks, formal textbooks refer to vector calculus, what they're referring to is the stuff that we're coming into now. The stuff that we have been doing is multivariable calculus. The vector calculus theorems are these three big fat theorems that we're heading into. Well, yeah. Green's theorem is related to double integrals, and Stokes' theorem is related to surface integrals, and Divergence theorem is related to triple integrals. And so there's a very close pairing. But formally speaking, vector calculus is the section that we're going into now. So the upcoming three theorems Green's, Stokes, and Divergence. Divergence theorem is also called Gauss's theorem. Refer to certain kinds of curves and regions, which we should define. So let's do that. Okay, so first of all, a simple closed curve. A simple closed curve. Oh! Some very strange things can happen sometimes with this stylus. Okay, a curve is simple if it does not intersect itself anywhere between its endpoints. A curve is simple if it does not intersect itself anywhere between its endpoints. So if you want to actually write that symbolically, you'd say r of t1 is not equal to r of t2 for T1 and T2 between the endpoints. Okay, so that would be symbolically writing what I've just said in words. A curve is closed if the endpoints are the same. So if R of A is equal to R of B. Okay, that's obvious, like a circle or something like that. Okay, and then just to give some pictures to back that up, something like this is simple but not closed. Something like this is not simple and is also not closed. Something like that is not simple but it is closed. And then something like this, well, as long as they join up, that is simple and closed. Okay, so it's just a loop of some kind. Question?
What if it goes back and forth on a straight line and has no sort of enclosed area?
Then it would be simple and not closed.
Not closed.
Yeah, if it's along a line. So basically like a line segment.
And if it came back on the same line?
No, you'd look at the actual, you'd look at the picture that it makes, really, more than the motion of the particle along it. Yeah, so it would still be even if the motion of the particle in a sense is closed because it comes back to where it started, the curve itself would be simple but not closed. You're referring to the geometric objects of the path rather than how something moves along it. Okay, so that's one thing. A simple closed curve, that's a term that we're going to come across. You need to know what it means. And then we have something called a simply connected region. Okay, a region R is connected. I quite like these definitions. Certainly this connected region, I find them quite evocative. A region R is connected if any 2 points in R can be joined by a path which lies inside R. Okay, a region is simply connected. So that's if it's connected. Simply connected if every simple closed curve, which we've just defined, in R encloses only points which are in R. Okay, and then once again I'll draw some pictures to back up what I'm talking about there. So a region that actually consists of bits. Let's say these two blobs together are jointly called R. Okay, that's your region, those two blobs. That's not connected. Because if you choose a point in the one blob and you choose a point in the other blob, you cannot join them with a path that remains entirely within R. You'd have to cross over that gap in between somewhere. So if that is your entire region, then this is not connected. Okay? And then something like this, a blob with a hole in it. Blob with a hole in it is not a technical term that you will find in a textbook, but there you go. That is connected, because if you take any 2 points in the shaded region, you can join them with a path that never strays outside the shaded region. However, it is not simply connected, because what about a loop that goes right around that hole? Such a loop would be enclosing points that are not in R. So this is connected because you can travel from one point to another point without leaving the shaded region, but is not simply connected. Because it is possible to draw a loop where the loop itself is entirely in R, but there are points inside the loop that are not in R. And then what you would want is basically a blob with no holes in it to be a simply connected region. Okay. Another term that we need to cover is positive orientation. Okay, the boundary of a region is positively oriented if, as a particle moves along it, okay, so this is the boundary of a region. Okay, so we have some sort of blob, whether it's got holes in it or not, and you have the boundary, and you have some particle moving along it, some little ant walking along this path. As a particle moves along it, the region remains on the left. Okay, so you're a little ant walking along the path. The region has to be on your left. Okay? There you go, regions on your left, you're walking round and round and round. Now this sounds the same as anti-clockwise, because look at that blob on the right over there, the top right. If you're a little ant walking along the boundary and you want the region to be on your left, you'd be walking anti-clockwise. So why don't we just say anti-clockwise? It's because of regions like the one in the middle, that the blob with the hole in it. Because there, you could have two little ants, one that's walking around the outside and one that's walking around on the inside. And the one that's walking around on the inside, in order to keep the region on its left, would have to be walking around clockwise. So positively oriented does not necessarily mean anti-clockwise. It means keeping the region on the left. But seeing as most boundaries are in fact outside boundaries rather than inside boundaries, positive orientation and anti-clockwise are usually the same. But positively oriented is the fundamental definition there, and it means keeping the region on the left. So now I'm just writing essentially what I've just said verbally. The positively oriented boundary of a simply connected region so simply connected, so that's the blob at the top right there, goes around anti-clockwise. The region shown in the middle diagram above has its boundary positively oriented. Sorry, I'm just abbreviating there. Positively oriented. If the outside curve goes around anti-clockwise. Oh, I beg your pardon, I don't usually bring my phone into the lecture theatre. Should put it on silent. The inner curve goes around clockwise. Question, yes?
What would happen if, like, say the one way and the other way, such that, like, we're describing a region which seems to have both positive and negative orientation?
Look, a region can have, okay, so a curve can have, a boundary of a region can be positively or negatively oriented, and it's not really a big deal. But the wording of Green's theorem and its friend theorems require boundaries that are positively oriented in order for the theorem to apply.
So we're looking at the boundary of
the region, not the region itself. Okay. Yeah. So if you have a region and its boundary is defined, and its boundary is defined in such a way that in fact it's going around negatively oriented, then that's fine. But if you want to apply Green's theorem or one of its friend theorems to that region, you would need to then keep that in mind and change the orientation of the boundary. But we'll deal with that. We'll deal with that when we get to exercises. The Green's theorem exercises of the regions that have holes in them. So 33 and 34. Yes? No? 33, yes. And then 39, 40, and 41. And 42, in fact. Those are all regions that have holes in them. Yes?
When you think about the direction, is that the direction of increasing parameter?
Yes. The direction of increasing parameter, yes. As if a particle were moving along it and time was moving on. And t, your parameters like time, yeah. Okay, all right. So those are some terms that we're going to be using: simple closed curve, simply connected regions, and positive orientation of boundaries to regions. Can I do a page jump? But now we're moving on to something perhaps a little bit more exciting, which is the operations div and curl. And I've told you already, although you may have forgotten, early on in the course I said there's an absolutely wonderful book on vector calculus that's called Div, Grad, Curl and all that. Div, Grad, Curl and all that, by somebody Shea. I can't remember the first name. And the library has 2 copies, and I still haven't got my own copy, but I will be getting my own copy, and it is laugh out loud funny. You wouldn't think it could be, but it is. It's a really wonderful book, and I've shown it to other people, and they've gone, yes, I know that book, it's a wonderful book. So if you're the sort of person who likes reading math stuff for fun, you can go and find that in the library. But there you go. Okay, so let's define div and curl. Let's say we have a vector field where its component functions are called P, Q, and R. Okay. The divergence, or div, so div here is short for divergence. The divergence of F measures the outward flow of fluid from a point. So you can think, and we're not going to see this for a little while, but you can see that div is going to be related to flux, because it's to do with flow of fluid from a point. Outward flow of fluid from a point. Sure, it's a bit alliterative there, from a point. Now you can derive the formula for div. I'm not going to derive it, but the way you do derive it is the formula for divergence is derived. See, this is the correct use of the word derive. Derive doesn't mean differentiate. The formula for divergence is derived by imagining a tiny box at a point and determining the total flux out of the box. So you can go and look up derivations of this formula. I'm not going to do it, but the result is div of f. So div is short for divergence. If I ask you what's div f, or I ask you what's the divergence of f, it's the same thing. And it's a very easy formula to work out. It is simply the sum of the derivatives of the components of f with respect to the 3 variables. Well, I'm assuming here f is a function of 3 variables. I suppose it could be a function of 2. But we generally deal with 3 dimensions. Yeah, it's flux out of a point. Yeah, it would be most unusual to look at this in 2 dimensions, although I suppose simply symbolically one could. But it makes sense just in real life terms to look at it in 3 dimensions. So f is a function of x, y, and z. P, Q, and R are functions potentially of x, y, and z. dp by dx plus dq by dy plus dr by dz gives you div f. Okay, so I'll talk about div, but let me introduce curl first. The curl of f is a measure. Sorry, I know my capital F's don't look terribly much like F's, but yeah, whatever, we all have our weaknesses. There we go. The curl of f is a measure of rotation, sorry, that doesn't look a lot like rotation, there we go, rotation, or swirl. I have seen the word swirl used in some textbooks. Rotation or swirl about a point. It can also be called rot, F for rotation. I'm not going to be using that term, but you might run into that somewhere. It's all to do with how swirly it is, how much it's rotating, how much it's curling, I suppose. So it's all about how swirly your fluid is. Okay, your phone is not going to be writing your exam for you, but there we go. One of the joys of being a university student is you have this power over your own life to read your phone in class if you want to. Or to bunk class entirely. Just look around at this semi-empty lecture theatre, which is supposed to be full. Our colleagues are still in bed. The formula for curl is determined, this time not by imagining a tiny little box, but by imagining a tiny little wheel. By imagining a tiny wheel in the fluid at a point and calculating its angular momentum, and then when you've done that derivation, you end up with a constant times by a thing, and then it's that thing that we end up calling curl, which is then interpreted. So I'm just kind of giving you a little bit of a glimpse into how these formulas are derived without actually deriving them ourselves, which we don't have time for, which is then interpreted as a constant multiplied by curl. And I suppose the reason why I'm giving you this sort of glimpse into the derivations is because I want you to get a feel for what these things are measuring. One is measuring, if you have it's measuring flux, essentially. It's measuring flow out of a point, so it's measuring sort of flux through a tiny little sort of thought experiment box at a point. Whereas the other is imagining if you put a little wheel down in your fluid, is it going to spin? If your fluid is all flowing in an absolutely linear direction, you put a little wheel down, like a little mill wheel or something, it's not going to spin. But if your fluid is twisty, then it is going to spin. And how fast is it going to spin? And is it going to spin faster in some spots than in other spots? And this is important information. It's interpreted as a constant multiplied by the curl, where the curl itself is, curl F equals, okay, a rather clunky looking thing. However, I'm going to write down the clunky thing, but there's an easy way of working it out. Here is the clunky thing, dr by dy minus dq by dz, comma, dp by dz minus dr by dx. Don't panic. It's actually fine. dq by dx minus dp by dy. Okay. Alrighty then. So we have these two formulas, the one that's at the top of the screen and then this rather awkward looking one at the bottom here. And they both can be worked out very quickly and fast using the dot product and the cross product between f and something that we call del, or the differential operator vector. I mean, one thing you have to admit, this course is giving you some good vocabulary to impress your humanities friends at parties. But then, of course, they'll turn around and they'll use various sort of philosophy or psychology or politics or economics terms at you, and then you'll be floored. Okay, so we're going to define something called the differential operator vector. It's a vector that has as its components the differential operators. And we draw it as a triangle. And it's not a vector that can ever stand by itself because it's an operator vector. Its existence is manifested by its operation on other things. It exists in order to act on things. Like the word log. Log is nothing by itself. It has to be log of something. Cos of something. D by dx of something. Okay, so those are operators. And we call this thing del. If we define the differential operator as that thing and choose to interpret the dot product not so much as, or in fact the cross product as well, not so much as a product, but as an operation, a dot product, as an of operation, like log of something, cos of something, the derivative of something. If we choose to interpret the dot product as an of operation rather than as a product, rather than as a product, we can define, sorry, this period is turning out to be very talky for me, but don't worry, the emphasis will shift at some point. We can define div f as del dot f and curl f as del cross f. Yes?
Can you explain, or could you explain how we interpret the dot product as an operation rather than...
I should probably do a calculation to demonstrate that, and I am going to, let's have a look. So basically what that means is, if you have f, let's say f is, let's make up an f, xy, x squared plus z squared 2yz. There we go, there's an f. And I want to work out del dot f. Then what I do is I would, well, div f is sufficiently easy that you don't really need a trick like the dot product to remember it. Basically it's d by dx of xy plus d by dy of x squared plus z squared plus d by dz of 2yz. That's nice and easy. It's the curl that gets a little bit more complicated. What would that be? That would be y plus 0 plus 2y, and that would be my div f. What about my curl f? My curl f I would do like a dot product, except it's not a product. So what I do is at the side of the page, just like I would ordinarily do a little cross product, little side of the page calculation, I always start writing from the bottom. xy, x squared plus z squared, 2yz. I'm running out of space on my page. Do it over here instead. xy. Okay, you know how I like to do cross product by now. I repeat the I and j terms, d and dz. Okay, I'm going to do a cross product now. Alright, so I don't do d by dy times by 2yz, I do d by dy of 2yz. That's 2z. Minus. I don't do d by dz times by x squared plus z squared, I do d by dz of x squared plus z squared, and that's 2z. Oh, that's cute. Come on, that was completely accidental because I made this example up. Okay, d by dz of xy, 0. d by dx of 2yz, also 0. d by dx of x squared plus z squared, 2x. d by dy of xy, y. So it's like a cross product, and every time when you would say multiply, you say of. Couple of tricks there. First of all, notice how, did you notice I wrote the bottom line first? That's because my components of f are often quite big and chunky, and I want to make sure I have enough space to write them. And if I wrote my dx, dy, dz first, I've learned from experience I often end up with not enough space to write my components of f. So when I do this, I always write my components of f first in the bottom line, the dx, dy, dz above them, properly spaced, and then however you do the dot product. This is how I do it. It's how I was taught by my physics lecturer when I was in first year here at UCT, and that's just the method I've used ever since. Some things stick forever. But choose your favorite way of doing the cross product, except it's not a product, it's an of operation, it's a differential operation. Okay, if you can do cross product, you should be able to do this. Okay, let me carry on with more talky. Where am I? Okay, here we go. Divergence. Question. Did I get it wrong? 2x minus x, in fact. Thank you. What was I? Red. Thank you. That was a careless mistake. And then, of course, one can simplify that 0, 0x. That was quite a nice example. Nice and simple. Thank you for pointing that out. Divergence is a scalar function. Notice the thing that we got when I did div f. I got y plus 2y. Well, that's 3y. That is a scalar function. Divergence is a scalar function. Curl is a vector function. Okay? Divergence is how much fluid is flowing out of a point. There's no directionality associated with it. It's not a vector quantity. Curl is to do with spin. It's going to have not just magnitude, but it's also going to have a direction component to it, a direction feel to it, sense to it. Okay, a few little interesting facts. Div f equaling 0 means f is, and the words that are used are incompressible or divergence free. Just some language. If curl f is equal to 0, and notice how the one 0 is just a 0, but the other 0 is the 0 vector, means f is irrotational or curl free. Okay, I'm going to do a page jump, but I will scroll back. Okay, what else have I got here? It can be shown, this is kind of like a little cute fact, it can be shown that, in fact it's not hard to show, div of curl f equals 0 for all f. Doesn't matter what f is, you work out its curl and then you work out the divergence of the curl, you get 0. It's kind of like a cute fact. Don't think it's particularly important. Theorem, given without proof. If little f is a function begins with an f, is a function of 3 variables with continuous second order partial derivatives, which most do, it's not really a special thing. Continuous second order partial derivatives. Then, and this is a very handy fact, curl of grad f equals 0. Okay, f is a scalar function. It's some function like x squared plus y squared plus e to the z. Okay, it's a scalar function. You can work out its grad, okay, which is its gradient vector. So it's a vector that's made up of all its partial derivatives. And so because it's a vector, you can then work out its curl. Turns out that you always get 0. So what that means is that if the big F, whose curl you're working out, is a conservative vector field, its curl will be 0. Okay, so can you see that? Big F is a vector field. We can make up all sorts of vector fields. I made one up in the red, just scrolled off the screen there. You can make any up. You can make up infinitely many vector fields and call them big F. But only for some of them are they interpretable as the gradient vector of a little f. And those ones we call conservative vector fields, and we call little f its potential function. And it turns out the curl of those big f's, that curl is 0. So that is a trick to working out whether your big F is in fact a conservative vector field or not by working out its curl. Except what I just said now was in fact the opposite, because here I've said the curl of a conservative vector field is 0. Does it necessarily mean that if the curl is 0, your vector field is conservative? In fact, it does. And that is a second theorem, again given without proof. Question?
The statement that the second order partial derivatives, is that like only f, or is it second order or lower? Can we not have a conservative vector field that has less than the second order partial derivative?
I'd have to think about that. So you have a vector field, it's a conservative vector field, its first order partial derivatives are fine, but its second order partial derivatives are not fine, and your question is, can such an animal exist?
What we just did not worry about that.
In order for this statement to be true, it would have to have conservative, the curl would, in order for curl to be 0, it would have to have continuous second order partial derivatives, but whether it's possible to have a vector field that is a conservative vector field and yet does not have continuous second order partial derivatives, I'd have to think about it. I'd have to play with some examples and see if it's possible.
So, I mean, could we replace that statement with conservative vector fields have curl of 0? Is that what we
Well, that would be the equivalent statement, wouldn't it?
I mean, is that true?
It probably is true, yes. Probably is true, yeah. If f is, okay, we've only got a couple of minutes left. Let me finish writing this, and then tomorrow we can jump straight into some examples. If f is a vector field defined on R3, whose component functions, defined on R3 means it's got 3 component functions. It's a 3D vector field, whose component functions have continuous, and in this case just doesn't say second order, continuous partial derivatives and curl f equals 0, which implies in fact that it's not equivalent. Then f is a conservative vector field. So simply put, this says that the implication works both ways. Given a conservative vector field, you can, if you know it's a conservative vector field, then you can know that its curl is 0. But it goes the other way as well. If you have a vector field whose curl is 0, you can know that it is a conservative vector field. So the implication works both ways. And you must be careful in maths, because sometimes implications only work one way. Okay, one last sentence, and then we're done with all the sort of wordy stuff. Divergence and curl play important roles in applications of vector calculus to anything which is to anything which actually really flows, or anything which is modeled as a flow. To anything which is modeled as a flow, such as electricity, magnetism, and actual fluid flow. Okay, and that's the end of the righty-righty, and then I want to jump into some examples, which I will do tomorrow morning before running home for the first of the movers to arrive. So we'll do a bunch of examples, and then after that we will move on to Green's theorem.